Hi, everyone. Welcome to the second ECSPrecip quarterly seminar series. Before we start, I just wanted to give you a brief introduction of ourselves. We are part of AGU Precip Technical Committee, and AGU Precipitation Technical Committee fosters an inclusive and diverse community to promote research within the precipitation umbrella of hydrology. And we are one of the subcommittees of AGU Precip. And ECSPrecip stands for Students and Early Career Scientist Subcommittee. So we are striving to facilitate an open, inclusive, and collaborative environment for the students and young scientists in the field. We have several activities going on in our group, and quarterly seminar series is one of them. And we also have bi-weekly newsletters. One is Science Highlights, where we highlight papers that are related to precipitation. And also we have Precip Folks, and we're highlighting all the researchers who are in the precipitation community. And yeah, if you're interested in subscribing the newsletters, just contact us and we'll get you subscribed. And that's it for the introduction, and and Lindsay and Ishra will be the moderator of the seminar. So yeah, take it away, Lindsay.
Thank you, Yunjin. So we're happy to moderate today's session, and I will be leading like the first half, and then Lindsay will be taking over from there. So thank you all for joining our second seminar for this quarterly seminar series. We'll be hearing from 3 different speakers, and we are honored to be in the presence of 2 recipients of 2022 AGU Precipitation Award. We have Benjamin Goffin from the University of Virginia, Manish Dhasmana from the Indian Institute of Technology, and myself, Ishrat Dollan, a recent graduate from George Mason University. Each speaker will speak for about 15 minutes, and then we'll have like 5 minutes Q&A. And please type your questions in the chat box if you might have any. So the first speaker is Benjamin. So let me introduce our first speaker. Benjamin Goffin previously earned a Bachelor's of Science in Civil Engineering Technology from Bluefield State University and a Master's of Science in Civil Engineering from the University of Virginia. After working in the industry for several years, Benjamin returned to the University of Virginia to begin his doctoral research, funded through a Jefferson Scholarships Foundation Fellowship, and recently part of the NASA developed national program. His current work aims to advance the remote sensing of terrestrial variables and provide decision-relevant information on water processes that are unavailable by other means. So welcome, Benjamin. The floor is yours.
Thank you so much, Ishrat. Can you hear me fine?
Yes, yeah, we can hear you fine.
Great, and you can see the screen?
Yeah.
Great. Well, welcome to everyone. Welcome to the ECSPrecip Seminar Series. My name is Benjamin Goffin, and I am a PhD student at the University of Virginia. I'm honored to be invited to speak today. I'd like to thank everyone that's in the organization of the AGU Precipitation Technical Committee. My talk today is titled Changes in Extreme Precipitation Across the Meuse River Basin. Okay, so speaking about the logistics for my talk today, I'll just describe briefly the motivations for this research, the study area, period, and the data sets that we are using. I'll cover some of the results that I had presented at AGU, and then describe some of the limitations that we faced in this work, and then also describe the next steps that I'm excited about and provide some or offer some acknowledgement for the people who have contributed to this work. I'd like to say that some of these findings were provisional. Some of them were dated November or December of last year, and some work has continued beyond that. But I appreciate your feedback, and I think some of the things that I'll talk about today will be good content for conversation. So originally, I am from Belgium, and I was over there when there was a big rain event in the summer of 2021 with precipitation that is very unusual for the area, over 20 centimeters in certain places, which is the equivalent of about 2 months of rain in just 2 days. A part of Europe that was severely affected by this extreme precipitation and flooding is southern Belgium. 39 people lost their life. There was important property damage, also significant disruption to the infrastructure system. There were flooded tunnels, broken bridges. The railroad system was heavily impacted, and then power was lost. And I think about 50,000 people did not have power for a certain amount of time. And as these rivers are moving through towns and villages, they carry all sorts of contaminants. I appreciate the image that is shown there because normally there would be a creek in there with a sign that says no swimming, and now we see that the water is encroaching on this church. So this kind of sets the scene for the mindset I had when I began my PhD, and I wanted to learn more about precipitation and how precipitation can be extreme and how it might be changing in time. So the study area that I'm going to be concentrating on in this work is the Meuse River Basin. It originates in France to the south, and then it moves north, crosses about half of Belgium, and then collects water from Luxembourg and Western Germany before it goes to the Netherlands. So the area it encompasses is 36,000 square kilometers with 9 people over 5 countries, 9 million people over 5 countries. The data set that we are using in this work is MSWAP, the multi-source weighted ensemble precipitation. It has a 0.1 degree spatial resolution, and it begins in 1979. It has a temporal resolution at 3-hour time scale, but we used daily data for this work, and we looked at and reviewed data from 1979 to 2020. So we had exactly 40 years of data, which we split partly between 1979 to 1999 and 2000 to 2020. A term I will be using in this presentation is extreme, and there is a lot of discourse over the use of this word. When I think of extreme for the purpose of this conversation, I mean the most extreme values of precipitation in a given year. And so one measure of extreme precipitation in a year is RX1, which looks at the most intense event in a year. And so here I'm plotting the most intense, or the typical most intense day of precipitation in a year, and we see that it varies from about 25 millimeters to up to 40 millimeters. Another value that people sometimes look at is R95 percentile, and so that looks at the volume that falls in the top 95 percentile. And so here we see that it varies. It's an important amount, ranging from about 200 to 400 millimeters. And it varies similar to what we had seen with the top event. Something that is interesting to note is that precipitation is more important to the east of the basin, where elevations is higher. And then one last variable that I'd like to talk about is R95 percentile as a ratio of the total annual amount. And so what we see here is that the values that were, or the areas that were previously blue are now red. This is because some of these places to the east, in the Ardennes region or the Eifel region, have more annual precipitation. And so even though they have a great amount of precipitation in the 95 percentile, as a fraction of the total annual precipitation, that ratio is down. And so we see that that ratio across the whole watershed varies from about 30 to 40%. So that means that about 1/3 of the precipitation for the entire year is in the top 95 percentile. Once we have reviewed kind of the general numbers for the basin, I think it's helpful to look at shifts through different time periods. And so there is the first one from 1979 to 1999, and then a second 20-year sequence that we looked at from 2000 to 2020. So what we see is that across these three variables, it appears that precipitation extremes are shifting towards higher values. That's true of the annual maxima, the 95 percentile, and the contribution of the 95 percentile to the annual total. Now, something that's interesting too, I think, is not to think about a shift, but maybe to look at these changes, assuming non-stationarity. So here we are looking at trends. We are computing a Mann-Kendall test, and what I am showing here is the tile descent slope using a threshold p-value of less than 0.05. So what we see in the leftmost plot, the annual maxima, we find very few trends. There must be a lot of variation from year to year. And then in the top 5 percentile, we see that we have certain areas that are affected or that show a significant trend year after year in how precipitation extremes might be changing. I think things are getting more interesting when we look at the rightmost plot and we see the role that is played by the extreme precipitation with respect to the annual precipitation. So there we see that large areas of the river basin appear to be getting more precipitation in their top percentile. And it might be in the range of 1 to 3% increase for each decade. Keep in mind that we were at about 30% to begin. And so I've put some more thought thinking about the annual distribution of daily precipitation. Previous studies think about it in different measures, but sometimes people will talk about how there are more frequent and longer dry spells. And then there is also more intense rainfall, more frequent extreme rainfall. And so these different things are affecting the uneven distribution of precipitation, and potentially the precipitation is getting more skewed, or the annual distribution of daily precipitation is getting further and further skewed. The measure that I showed before, where I showed a fraction of the top percentile that contributes to the annual precipitation, is one way to think about it. So it's the contribution from top days. Another way to think about this is to think of the number of the wettest days it takes to reach a certain contribution, like a certain fraction of the annual precipitation. So this is something that has been talked by Pendergrass and Nuti in 2018. And I based some of my work for AGU on this concept. And so this is what I want to elaborate on a little bit. What I am showing here is the wettest days in the year that it takes to make 50% of annual precipitation. And so a mean value between 1979 and 2020 is around 35 days or so for this watershed. So it takes roughly a month of daily precipitation to get 50% of the water that you get in a year. We see that it changes across the basin some, but that's kind of the idea. When we think of a shift between the first 20 years of the time period and the following 20 years, we see that certain areas are pretty dark in the blue. Potentially, we have a shift that's on the order of about 6 days or so between those two time periods. I think things are getting more interesting when we think of that linear trend, that monotonic trend through time. And so we see that for each decade that we move along through time, potentially we've got a change that is in that amount of the wettest days making 50% of the precipitation, a change that would be on the order of about 2 to 3 days, fewer 2 to 3 days. So it takes fewer days to get to a certain amount of precipitation in a year for this particular basin. This is, I think, what I appreciated more about meeting with some of the people from the AGU Precipitation Technical Committee, the discussion that followed afterwards. we spoke about some of the limitations, and I'd like to speak a little more about that. So some of the plots that I showed today, they show trends, and they use a static p-value of less than 0.05. One thing that I learned in that process is that potentially when you take a test again and again and again, there is an amplification of the false discovery rate. And so this is something that I've addressed in the last month as I made my way further with this work. So we've adjusted the significance level. Something else that's interesting to think about is that MSWAP is a gridded data set, but in order to get there, data from a station network was interpolated and crossed with other data sets. And so potentially we've got bias in the data set due to uneven station network. So something that we've done is looking at how the values that we found compare with other data sets as well. And then something that we were particularly interested in is that WD50, the wettest days to 50%. We studied some more and looked further into the sensitivity of this measure as we look at data prior to 1979 and expand through time, but also look at this study beyond just the Meuse River Basin to a larger continental scale. And so we see if these findings are still holding true or not, and if or what we can learn about other regions and how they compare with changes in other places. I like this image here particularly. I think it shows the resilience of some of the people that were impacted by the flooding. And it also talks about collaboration across borders in Europe, as the firemen you see there are from Italy and they came to the rescue of people in Belgium. So I like this approach, and I like the fact that I was able also, in the aftermath of this disaster, to connect with people within AGU and to get this work started. There are more ways to continue this work. Some people have looked at not the wettest days to 50%, but the wettest hours in a year to 50%. And so potentially looking at finer temporal resolutions can add value. There is also something to be said about how the wettest days contributing to the annual contribution might have seasonal patterns and which season contribute most. Something that was interesting about the flooding that happened back in 2021 is that it happened in July, and it didn't happen during a drought with very dry condition on the ground, but it happened in a particularly wet summer. And then something else to consider would be how these wettest days might take place in series or as a sequence with back-to-back events. This is also something that happened in the summer of 2021, where there was a first flood that happened around mid-July and another one that followed later in the month. There were many people that contributed to this work. I'd like to give a shout out to my research advisor, Professor Venkataraman Lakshmi, and then two of my colleagues, Dr. Prakrut Kansara and Dr. Younglok Kim. I'd like to acknowledge that I have received funding from the University of Virginia, the Jefferson Scholars Foundation, and that my travel to the AGU conference was made possible by NASA Develop. I've also put here my information, my email address, LinkedIn, and my website. I'd be really happy to connect with all of you. I anticipate that this work will be published in the coming weeks, and so I'll be happy to follow up and point you to the publication. Thank you so much.
Thank you, Benjamin. So, okay, so there is a question from Lisa. The question is the data set you used based on rain gauges and interpolated into 0.1 degree grid?
It has many inputs that go into it. Rain gauges is one of them. It has other gridded data set. It has satellite data, and I think another input into MSWAP is reanalysis data. So many product go into it, as I understand it.
We haven't received any question. So I think we can take a quick question and then we can move forward. So there is a
Satellite.
follow-up question. Is like, do you know which satellite is that?
Not on top of my head.
Okay, so since we don't have any question.
I have a question. So,
Yeah, sure.
can I ask a question? So thank you for the presentation. So I wanted to ask you that you mentioned some non-stationarity you have considered by calculating RX1, right? Have you considered non-stationarity calculating the RX1?
It's breaking up a little bit. I heard you say whether or not I considered non-stationarity when looking at the trains.
Yes, you have calculated RX1, right? So you have mentioned in this slide number 2 or 3, that non-stationarity is considered. So my question was that, did you consider time-dependent variable or something like global mean temperature?
Oh, I haven't looked at precipitation with respect to how temperature is changing. The test that we've done initially, we were looking at linear changes with respect to time, and then we switched to monotonic changes. So this is how we are approaching the non-stationarity in the data with Mann-Kendall test.
Okay, thank you.
Okay. So yeah, I think Lindsay will take from here, and there are a couple of suggestions from Lisa for Benjamin. You might try to see in the chat box. Thank you.
Great. Yeah, I see the comment from Lisa with GPM iMerge. So this is kind of where we are going with this research. We've looked at other data, other graded data, other satellite data, just to make sure that our findings hold strong across different data sets. And you know, when I spoke about this the last time around with the AGU Precipitation Technical Committee, this was their input. So I thank them for that. I see also, have you tried to see what kind of correlation there is in your study area with drought days preceding the extreme wet days? No, this is not something that we have looked into just yet. I think it's interesting, and there is an important body of literature about how these extremes can flip back and forth. But as I said, for this particular case, the flood happened in a very wet summer, and so conditions on the ground were saturated, but they were not. They were not in a state of drought. Thank you so much.
All right. Yeah, thanks, Benjamin. That was great.
Thank you.
And next up, we have Manish. So Manish is a PhD research scholar at the Interdisciplinary Program in Climate Science Studies in Bombay, India. His work is on the probabilistic attribution of extreme flooding events on a regional scale, and his research aims at carrying out attribution analysis for hydroclimatic events in India with a focus on flooding. So Manish, if you want to go ahead and share your screen. Leave. Yep. All right. All right, looks great. Go ahead and take it away, Manish.
Thank you for the introduction. So I'm Manish, a PhD scholar in IT Bombay. So the topic of my talk will be the evaluation of SIM6 model for the extreme precipitation. So, you can see that two keywords are there in my introduction: the SIM6 model, which are the GCMs, and the extreme precipitation. So why we need to evaluate the extreme precipitation and the GCM models? Because we know that, I mean, these extreme precipitation are the responsible for the major flooding event around the world, and we want to use that information from the climate model, that how the mechanism are changing for these extreme precipitation, so that we need to evaluate these models that so that we can use that model impact studies. So I'll begin my presentation with the I begin my presentation with some of the background in the state. So on the left hand side, you can see that there is a situation for the last year flooding in the Assam, one of the state in India. You can see that 2 or 3 days of rainfall would take how much impact they have created. That around 28 districts were affected in the flooding, and most of the river was flowing above the flood level, and 3 rivers are flowing above the danger levels. These number of villages were impacted by the flood, which is, I mean, it was only 3-day event that has caused this much of damage. And in the middle part, you can see that some of the pictures from the Bihar flood, and in the middle and the bottom here, you can see that this is the picture from the last year Pakistan flood, in which the 1/3 of the country was inundated, and so that was the kind of extreme events I focus on. And we have a literature on these also, that why they are increasing, why the widespread extreme rainfall event in South Asian domains are increasing. And some of the paper are trying to disentangle the role of anthropogenic climate change in this kind of precipitation events using the climate models. And these are the papers that I've looked into it. And one of the paper from the Hunt and Manon, which have checked the role of anthropogenic climate change for the Kerala flood, which is one of the major flood events in the southern India. So coming into the extreme events like extreme precipitation in the form of climate, in the left hand side, you can see that there's a temperature change related to last century, 1850 to 1900. You can see that the prominent trend in the global mean surface temperature, where in 2006 to 15, it is reaching around 1 degree, and it is projected to be reaching 1.5 degree in next decade. So what this global warming does, so this warming of temperature does, so this will increase the water holding capacity of the atmosphere according to CC relationship, and this will release more latent heat, and this will produce more heavier rain into the system, and this will increase the flooding and extreme weather condition, which will be more violent and consisting of the more compound events. Secondly, if you want to check that how much we are confident that how much human contributions have changed this impact. So first figure is from the IPCC AR6 report, in which you can see that South Asian region have the increase in the hot stream with very high confidence human contribution. Whereas if you see that South Asian domain for the heavy precipitation, you can say that only it is showing increase, but the confidence is limited due to the element. And why limited due to the element? Because there is no agreement between these local climate models with the observations, and the lack of observation. So, but the thing is, for the AR6 report, they have increased this confidence with respect to AR5 of the human contribution. So that will set up our background, that why we need the GCM simulations and climate model, and why we want to use them for calculating the changes in the extreme precipitation. So in the attribution study, one of the method, which we use is like using the climate model, in which we have the simulation with a which represent the actual world, which is called historical simulation, and other simulation which represent the counterfactual world, which is a natural simulation. So that we can directly calculate the changing probabilities or changing frequency in the both the simulation, and we can attribute the event. So that all the studies are largely dependent on the climate model, and it is very important to provide that evidence that models which is used in the study are fit for purpose, so that we model evaluation. So coming to the so for this present study, I have evaluated around 11 GCs model with their native resolution. So you can see that they have very different resolutions, which is very coarser in nature, and they are available. The historical run is available from 2014, and the reference data set which we have used is observed IMD graded data, which is derived from the interpolated data set from the stations data. So with that we have used as a reference set, and we have used the indices which is defined by the ECSPrecip precipitation indices, which are given by this agency. So these are the indices which we have categorized into different categories. First, 4 basic categories like absolute indices, which is precipitate, annual total precipitation during wet days, and RX1B, which is annual maxima for 1 year. And other categories are intensity based, which is SDII, and other categories is duration indices like cumulative dry days and cumulative wet days. So these are the indices which we have considered for the period of 1951 to 2014 for the models as well as IMD data set. And we also have used two matrices, indices, just to take the model performance. So first index is the model climate index, which is used as the if we take the climatological mean of any index and subtract it with the observation, and that will be the root mean square error in that model. But if we normalize it, we will get the normalized RMSE. And the main thing here is that a negative of normalized RMSE in a data set indicates that the corresponding model data set is performing better than majority of CBSS model, because we need to have the ranking of the model, right? So that's why we need to have this kind of metrics so that we can rank them. So this normalized root mean square error can be taken as the model of climate index MCM. Likewise, we want to use the how if this model is able to simulate the variability across the model or not. So for that we are using interannual variability scale score. So that is that in that we are using the interquartile range, which is we are using this formula and again normalizing it. And again, if negative of and we normalize IVSS in the dataset is corresponding to the dataset performance better than majority CBSS model. And this will be calling as a model variability index for a particular model. So coming to the results. So here you can see that in the left hand side, this is the observation, which is the total precipitation in a year of a rainy day. So it's going from 200 to 4,000. But if we check the biases in the model in the right hand side, all the model which we have considered, you can see that most of the models are dry biases there of the order of 600 to 800. The CBSS models are underestimating most of the total precipitation. So these biases can be attributed to the inaccurate simulation of the mesoscale converter system, which is used in these models. But one thing is that there's one model which is, derived from the Indian agency is IITM ESM, which generally, we thought it will simulate cloud, but again, it is not simulating very perfect in terms of total precipitation. And if we check for the cumulative dry days index, so again, the most of the time we know that most of the GCMs tend to give the very low precipitation frequency, but it does not give the any dry day very. So so that is can be seen here because the underestimation of cumulative dry days. But again, for the IITM ESM, you can see that the bias is not too large. Same as the cumulative wet days. So the main thing is the wet days in that's the model like IITM ESM and MPI and Access ESM. They are performing little bit good in comparison to other models. So same with SDI. So what pattern which we are seeing in these these indices is that the region which are showing negative dry bias are consistent throughout all the indices. So that the main takeaway is that from that. So one of the most important indices is RX1D, in which we can see that the huge underestimation is there in the central part, which is the monsoon core region of the Indian monsoon. So same with the R95P. So coming to the relative performance of the selected CMIP6 model. So we discussed that the MCI would be, for the model, the negative of root mean square will be the performing better than the majority of the model. So you can see that these color which are negative are performing all the indices very well, but some of the model like INM and INM-CM4 is not performing well. So same with the interannual variability indices. So you can see that again, these two models are constantly not performing well for the most of the good indices, but here for wet days it is not performing well, but for the variability indices it's also not performing well. So these kind of metrics will be giving us the variability and the total climate indices. So if we plot MCI in the x-axis and MVI in the y-axis for all the models, so we will get a space in which we can rank the model. So we want MCI in negative and MVI in negative. So that model will be our good performing model. So you can see that the model lying in quadrant 3 will be performing good with respect to the majority of the model. So that we can rank them. So Miroc 6 and the IITM ESM are in the quadrant 3. So we can see that these models are performing in terms of climate or in terms of variability. So again, using these models to quantify the changes in the extreme precipitation with respect to and attributing to the anthropogenic scenario, what we have done here is that we have taken the two scenarios in the for these model. First one is natural scenario, which is like counterfactual scenario without anthropogenic emission, and the second one is the historical scenario with having all the emissions. So, and we have checked the change in the frequency and the change in the magnitude. So in the first left hand side, we can see that this is the change in the frequency of 100 year return period event. So these models are not showing very, for the historical and the not natural, these models are not showing very difference in them, and which is suggesting that there is very limited role of anthropogenic emission in the changing in the magnitude and the frequency the over Indian subcontinent, which is, I mean, kind of questionable because most of the observational studies have shown that there is a role of anthropogenic emissions in the changing extremes over the region. So, but if you compare all the changes in the frequency and the magnitude with the high warming scenario for the later decade of the century, like 2070 to 2100, and compare it with the historical, we can see that the increase in the frequency and the changes in the magnitude are very high. So that is because of the models are simulating, they are putting the emissions deliberately. And that is suggesting us that the model is getting extremes in the later part of the century, and with respect to the historical. So, but the thing is, these models are not representing the actual climate of the region, right? And the ranking is also not, I mean, not been done yet. Which model should be used to do this kind of analysis? So my motive was to do this ranking and to provide that why models are not able to perform well in the Indian region. So this is the summary of my study, that we have evaluated the models based on these indices, and there is a huge underestimation of the CDD and overestimation of wet days that indicate that models rain more frequently than in the reference of the observed data. And the regions of the dry ice in the STIA largely coincide with the dry ice in the Pacific, which is, I mean, obvious. So, and the two matrices we have calculated and we have tried to give them ranking, in which we found that ITM, ESM, Mirox and these IPSL, EC perform well related to other models for the Indian region. So this was our final, I mean, result. Thank you for listening.
All right, great. Thanks, Manish. I think we just have a time for a brief question. We have a question from Lisa in the chat. What kind of observations are included in the IMD dataset?
Yeah, so IMD has is the interpolated data using the station-based in the country. So we have around 6,000 stations in the around 6,000 stations. So after interpolating that, we get the gridded data at 25 kilometer resolution.
Great, thanks. And then just briefly from Jackson, do you know what makes the models like Merox 6 perform better? Do they have finer spatial resolution? Or
yeah. So the thing is, IITM. So if we can see that the Merox 6 is like, it does not have very good spatial resolution. Here you can see that it has a very coarse resolution, 2.5 in lat and long, but surprisingly, it is performing better. And we checked that. We checked with the temperature also, because it is also performing well with the temperature. But most of the get the fully answer of this, that why Merox 6 is performing well. But other model like ITM ESM has the better resolution than the Merox 6. But in the beginning, I didn't know that why Merox 6 is performing well. We have to check.
okay, yeah, great. Thanks so much, Manish. I think we better move on so that Ishrat has enough time. So if Ishrat, you want to get ready, I'll introduce Ishrat, the next speaker. She earned her MS and PhD in water resources engineering from George Mason University. And then her doctoral research focuses on understanding spatial temporal patterns of extreme precipitation across different scales, ranging from regional to continental. Ishrat is going to start her next role as postdoctoral researcher in the School of Marine and Atmospheric Scientists in Stony Brook University. So whenever you're ready, Ishrat, go ahead.
So can you see my slides? Is it in presentation mode?
Yep, looks good.
Okay, nice. Thank you. So today I'll be talking about like the historical and projected precipitation change in high mountain Asia. This is a part of my doctoral research. So there are other work I've done on other parts of the world, but today I will be focusing on high mountain Asia. So I'd like to acknowledge my collaborators and the co-authors for this work. And this work was part of the NASA High Mountain Asia project. So from Atlantic hurricanes to Indian monsoon, storms are getting worse and becoming more erratic, and which eventually dumping like record amount of precipitation in different parts of the world. So how should we prepare for this type of unprecedented extreme weather events? So to answer this type of question, we need to understand, it's essential to understand the changing characteristics of extremes. So I just pull up here some of the highlights from different papers and looking at different changes of extremes over different parts. But some of the studies have found that the intensity and frequency of extremes are increasing in different parts of the world, and we've seen that anthropogenic climate signals are also strengthening and expected to continue end of the century. So in general, there are like more intense hydroclimatic regime end of the century or like throughout the century. And one of the Intergovernmental Panel on Climate Change Assessment Report, like the latest one, Assessment Report 6, that documents increasingly intense precipitation over different parts of the lands. So to highlight the results from on your right, you see that there are like percentage of stations, global stations, that shows that more like significant shift toward wetter conditions than compared to the significant shift toward drier conditions. And these are completely from the ground stations and looking at the daily maximum precipitation in earlier decades. So that's kind of like the focus of my talk today. Like I'm focusing more on the upper extremes or the wetter extremes over high mountain Asia. So despite an increase in the global mean, there might be a change in most likely like the direction or strength of changes in precipitation at regional scale. And also it's important because there might be different subtemporal changes of the precipitation distributions. So what I mean by that, there might be changes in, say, for example, median distribution or like the upper quantiles. So that's why it's also kind of important. And I also try to understand how different distribution of precipitations are changing. So this is important also in terms of climate assessment or also like water management, especially for areas where it's like climatologically drought prone, but if you receive like heavy downpours, so I want to highlight that as well. So looking at the maps that represents like future changes in precipitation in average and extremes. The left map shows basically the average climate, and the right map shows the extreme. So mostly like the wetter or drier extreme. So if you look at the highlighted area, we see like northeastern side of the US, we see like the changes in mostly like dry to no change. However, we see that the same area has like climatic like extreme or wetter extreme periods. So that's kind of interesting. Look, so the average can be maybe in a dry zone, and then the extreme can be really in a wetter or a drier zone. So I would highlight these different types of changes over high mountain Asia. So high mountain Asia is basically a data scarce region, and also it's known for like the third pole because it has the largest ice mass outside of the polar regions, and it's called like Asia's water tower. There are many rivers like transboundary rivers all over this area, and in recent from basically satellite estimates, it's been shown that the frequency of extreme rain events are increasing, and also it's important also to understand about like flood attributes to this kind of extreme events. In over India alone amounts to about like 3 billion per year, which is basically 10% of the global economic losses. And also this area is influenced by different types of atmospheric circulations. Different seasonality, different types of seasonality is there. So basically, and also most important thing is that's basically coming to my next slide, is like this area has a very diverse topography and also different types of climate, like microclimates. And that's really make it interesting and also difficult to understand precipitation change at different scales. So, and also different studies shows that there might be some considerable interannual variability and inconsistencies and trends. So for example, if we have like longer time scale, the trends might have different directions. Maybe for a shorter time scale, it's completely can be very different. And since this area, and also another thing is these different studies highlighted only like different smaller parts of the area. So I think it's also important to have a study that comprises almost the entire area. And it's so the interesting part of the area is like this has like Tibetan Plateau, which is the highest plateau, and also surrounded by different mountains. So if you look at the west, there are like Karakoram, Hindu Kush mountain. In the central and eastern is like the Himalayas. We have like very low land areas in the India, in Bangladesh, and also like some parts in Pakistan is like high land areas. So in terms of the frequency and intensity of extremes, studies have found that it's kind of like projected to increase over this area, and also it's not consistent across different areas. So understanding from different literatures and also looking at different data sets, it's kind of, I had these two types of questions. I wanted to look at like how has precipitation changed in the recent past from 1990 to 2018, and how is extreme precipitation projected to change under two emission scenarios. So I'm using middle of the road, which is basically shear socioeconomic path 2 4.5, and another one is the like most pessimistic scenario is basically the fossil fuel development, SSP 5 8.5. So since there is like no consensus that we have the best product over this area, we're relying on a recently developed ensemble product, which I'll explain in the later slide, developed by Mina, and it's also part of the NASA HIMET project. We are using that ensemble product for looking at the precipitation in the past. And there is a bias corrected and downscaled product, basically a seamless system for prediction and Earth system research. That's a climate model simulation for these two emission scenarios, and it has 30 ensemble members. So basically, just to give a glimpse of the study area, I'm using multi-source data sets, not a single product. So I'm evaluating or like validating these data sets over this entire region using ground station data taken at 27 stations. And these are very discrete ground stations. Some of them are basically coming from Chinese Meteorological Administration. Some of them are coming from Nepalese meteorological stations. And you can see that the elevation map varies a lot. It goes from -192 to above 8,000 because some of the areas covering that tallest mountain ranges. So basically, we're using an ensemble product, which is basically coming from a consensus of reanalysis, ERA 5, and two satellite products, CHIRPS and iMerge. So what it does, just to give a brief idea, is basically we have an ensemble product. That's this ensemble mean. This is simply just like average of these three products. And then it does basically re-rank the EM based on the distribution of these three products. So it's been published, and if you're interested, you can look for more details. So this is from 1990 to 2018. And then I'm using at 5 kilometer scale. This product has hourly scale, but for my case, I'm using daily scale precipitation change. So LPM is basically used for bias correcting sphere. So that's why we are using sphere. And like I said, it has 30 ensemble members. And I'm also using the same resolution, like 5 kilometer and daily scale, and for different periods of the time. So I'm just sharing a few of the results from this analysis. So looking at this annual average precipitation, the brown represents the drier pattern, and the water is represented by the blue color. And so this is basically from 1990 to 2018. Only the significant trends were highlighted in the markers. So basically, downward triangular shape represents decreasing pattern, upward represents increasing pattern. So in general, what we see that like clustered of regions mostly on northwest and southeast has a higher decreasing pattern, mostly at annual scale. However, over like the lowland area or like the southern flank of Nepal or like Himalayas, and also like eastern part of Pakistan or mostly like central part of India, we have seen that increasing pattern at annual scale, but most of them are not statistically significant at 0.1 alpha significance level. So we have only tried on one significance level for this study. So I also looked at like seasonal patterns. So basically the left map shows summer precipitation that goes from June to September. And for the right figure shows basically the winter, which is from December to February. And so that same thing, I did some statistical significance over this area using 0.1 significance level. And if you can see from the summer precipitation, we see basically like eastern Pakistan or northwest India, also like southern part of Nepal, we see most likely like increasing precipitation, mostly like summer increasing precipitation. And this is like accumulated summer precipitation. But most of the area we see like the same pattern from average precipitation. We see that decreasing pattern of northwest and southeast part of the area. And looking at the winter precipitation, we see there is like kind of east-west gradient of decreasing pattern. Some of them are statistically significant, and eventually like the Tibetan Plateau, we see the winter precipitation is decreasing. Most of the areas there are like no change kind of thing, like mostly so this is kind of a lowland area, like Tarim Basin. And we see also some parts of India over there is no change in winter precipitation. So then I look at the change of 99th percentile. So basically this 99th percentile represents the wettest pixel and changing the wettest pixel over the domain. And so it's represented in percentage. So basically, since the LPM is used as a reference product to bias correct and downscale the sphere. So we have been using this as a reference product, and it's been shown on the map. So the dashed black line represents the LPM. And that's basically showing changes in top 1% precipitation. And then the shaded region, like basically the orange shaded region represents the historical precipitation from sphere. And we see that LPM is kind of encapsulated by the ensemble spread, but some of the years it cannot capture the LPM product. And the average is kind of showing mostly like a smooth like changes in terms of like when we are averaging all the ensembles. Looking at the future from 2015 to end of century, we see mostly like the shaded regions, the gray shaded regions represent the SSP 58.5, the fossil fuel development, and then SSP 24.5 is represented in the blue shaded region, and the dashed lines are basically the ensemble average. So, and up until like 2060, the ensemble average, both coming from these emissions, we see almost similar changes, but however, towards the end of the century, they kind of diverges, but still having like positive change in this index. So some of the key findings are, we've seen that the average trends are increasing mostly over lower elevation ranges, but not all of them are significant. And we see some localized summer trends and fewer statistically significant regions compared to the decreasing ones. And we've seen that like heavier daily rainfall, mostly like the top 1% change shifted basically and driven by the anthropogenic radiative forcing 8.5. So in general, what I've learned from this study, because this area is very vast in terms of elevation and the seasonal patterns are very different. So basically like seasonal patterns, this elevation gradient and different precipitation regimes characterize these trends at this 5 kilometer scale. So mostly like local physiographic conditions account for this kind of precipitation patterns. So this slide, last slides kind of is like to kind of connecting these different climate extremes, climate crises and extremes in a way that if we look at the left map or like the figure, it shows like climate vulnerability that's coming from like socioeconomic or like other modeling, like ecological and demographic modeling. And we can see that different parts of the world is having like high impact zone in terms of climate. So basically, these areas are important to understand how they are impacted by different parts of the, like, different distribution of extremes. And also like multi-source data sets have the potential to map these regions, because over this region, not a single product will perform better. And we haven't found that from the literatures. And also the right map, it's interesting because there might be some areas, especially over like this Himalayas region, rain triggered landslides are kind of frequent. So it's also interesting and also important to understand how these heavy downpours, or like, so something happened like last year in Pakistan in 2022. So how this type of event will impact this kind of cascading hazards over this area. So that's all from my end. So I would like to acknowledge like NASA High Mountain Asia team for funding this project, and this was like part of my PhD or like doctoral research. So thank you all. Thank you for your time, and I would like to take any question if you have.
Oh, great, thanks, Ishrat. Looks like it's a little bit after 1, but if you have some time to answer, just looks like Lisa and Jackson both wanted to know if you've examined the change in snowfall.
No, in the study, we haven't looked at the snowfall changes. But yeah, there are other groups of this project. They are looking at this cryospheric change and different types of snowfall changes. Yeah, definitely.
Okay, great. I actually had a question. I just wanted to, I don't know if I missed it, but I was wondering how your ranking system worked for your LDM. You mentioned that you re-ranked it, but I wasn't quite sure how that worked.
So this is kind of like I don't know, can you see my slide? Okay. So the ranking, this is done by the author is listed here. So basically what this is, they have like different radius. So they tried for different radius. For this study, there was like 25-kilometer radius, and basically there is a ranking algorithm that basically for example, you have a pixel, and then you take a radius of 25-kilometer, and you pick all the distribution from this 25-kilometer radius, and then based on this ranking algorithm, they will replace this ensemble average from these 3 different product. So does it make sense? So basically, there is kind of an algorithm that goes behind this calculation, kind of re-ranking the average.
Okay, yeah, interesting. Did we have any other questions? All right, looks like we're done. If we just want to thank all of our speakers again. They were all great talks, and I look forward to seeing you all at the next quarterly seminar series. So